When we gaze up at the night sky, we are often drawn to the brightest stars, those cosmic beacons that illuminate the vast expanse of space. Yet these stellar giants represent only a small fraction of the stars that populate our universe. The true rulers of the cosmos are far more diminutive and far more numerous, the red dwarfs. Red dwarfs, as their name suggests, are stars much smaller and cooler than our own sun. They emit a faint reddish light, a testament to their lower energy output. Despite their unassuming nature, these stars are true survivors, with lifespans far exceeding those of their larger counterparts. In fact, some red dwarfs are thought to exist for trillions of years, far longer than the current age of the universe. This longevity, combined with their abundance, makes red dwarf stars prime candidates in the search for life beyond Earth. If life exists elsewhere in the cosmos, there's a good chance it's found orbiting a red dwarf star. However, the path to habitability around these stars is fraught with challenges, particularly the intense radiation and frequent flares that characterize these stellar objects. The allure of red dwarf stars lies in their potential to harbor life-bearing planets. However, the environment surrounding these stars present formidable obstacles to the development and sustenance of life as we know it. One of the most significant challenges arises from the intense radiation emitted by red dwarfs, particularly in the ultraviolet spectrum. UV radiation is known to be harmful to life, causing damage to DNA and other biological molecules. While Earth's atmosphere provides us with a protective shield against the sun's UV rays, planets orbiting red dwarfs may not be so fortunate. The proximity of these planets to their host stars, often much closer than Earth is to the sun, results in significantly higher levels of UV exposure. In addition to the constant bombardment of UV radiation, planets around red dwarfs are also subjected to powerful X-ray flares. These sudden bursts of high-energy radiation can strip away planetary atmospheres, leaving any potential life exposed to the unforgiving vacuum of space. The frequency and intensity of these flares vary depending on the age and activity of the red dwarf, but even a single powerful flare can have catastrophic consequences for a planet's habitability. To truly comprehend the challenges posed by red dwarf stars to the prospect of life, we can turn our attention to Wolf 359, a nearby red dwarf located a mere 7.9 light-years from Earth. This seemingly innocuous star, barely visible to the naked eye, serves as a stark reminder of the volatile nature of red dwarf systems. Using sophisticated space telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton, astronomers have observed Wolf 359 unleashing powerful X-ray flares, far more energetic than any solar flares ever recorded on our sun. These flares, erupting from the star's surface with tremendous force, bathe any orbiting planets in a torrent of high-energy radiation. The implications for potential life on planets around Wolf 359 are significant. The intense radiation from these flares could easily strip away atmospheres, leaving any surface water to evaporate into space. Even if life were to find a foothold on such a planet, it would need to contend with the constant threat of these stellar outbursts. While the picture painted so far may seem bleak, there are glimmers of hope for life around red dwarf stars. One potential saving grace lies in the very nature of these stars and the planets that orbit them. Due to the lower energy output of red dwarfs, their habitable zones, the regions around a star where temperatures are suitable for liquid water to exist on a planet's surface, are located much closer in than the habitable zone in our own solar system. This close proximity, while increasing the risk of radiation exposure, also presents a unique opportunity. Planets in the habitable zones of red dwarfs are likely tidally locked, meaning that one side of the planet perpetually faces the star, while the other side remains shrouded in eternal darkness. While this might seem detrimental, it could lead to the formation of a thick atmosphere on the planet's night side. This atmosphere, rich in greenhouse gases like carbon dioxide, could potentially trap enough heat to maintain a stable climate, even on the side facing away from the star. In essence, the planet's own atmosphere could act as a shield against the harsh radiation from the red dwarf, allowing for the possibility of liquid water and perhaps life to exist. While a thick atmosphere can offer some protection against the dangers of a red dwarf system, distance remains a crucial factor in determining a planet's habitability. Even with a substantial atmospheric buffer, Planets located too close to their host stars will inevitably succumb to the relentless onslaught of radiation and stellar flares. The key to survival in these harsh environments lies in finding the sweet spot, a distance far enough to mitigate the worst effects of the red dwarf's activity, yet close enough to receive sufficient warmth to maintain liquid water on its surface. This delicate balance defines the outer edge of the habitable zone, a region where the chances of life as we know it emerging and thriving are considered to be the highest. Planets at this optimal distance might experience a less intense version of the tidal locking observed on closer-in planets. While still subjected to periods of extended daylight and darkness, these planets would likely avoid the extreme temperature differences that could render their surfaces uninhabitable. This more temperate environment, coupled with the potential for a protective atmosphere, offers a glimmer of hope for life to gain a foothold in these seemingly hostile systems. The prospect of life around red dwarf stars presents a fascinating paradox. On one hand, the constant barrage of UV radiation and powerful X-ray flares paints a grim picture for the survival of even the hardiest organisms. On the other hand, the unique conditions of these systems, with their close-in habitable zones and the potential for thick, protective atmospheres, offer a glimmer of hope that life, tenacious and adaptable as it is, might find a way to flourish. The type of life that could evolve in such an environment would likely be vastly different from what we are familiar with on Earth. These organisms would need to be incredibly resilient to radiation, perhaps developing novel biological mechanisms to repair DNA damage or shield themselves from the harmful rays. They might also exhibit unique adaptations to the prolonged periods of daylight and darkness characteristic of tidally locked planets. If multicellular life were to arise in such a challenging environment, it would stand as a testament to the remarkable adaptability of life itself. It would also force us to expand our understanding of what constitutes a habitable planet, challenging our preconceived notions of where life might be found in the vast expanse of the cosmos. The quest to understand the habitability of red dwarf systems, like the one surrounding Wolf 359, is a journey into the unknown. These ubiquitous stars, with their immense lifespans and potential to harbor planetary systems, hold both promise and peril for the search for life beyond Earth. While the challenges they present are undeniable, the intense radiation, the powerful flares, the unique conditions imposed on their orbiting planets, so too are the possibilities. The ongoing debate surrounding the existence of planets around Wolf 359 highlights the difficulty in studying these distant systems. While tantalizing hints suggest the presence of at least 2 planets, further observations are needed to confirm their existence and characterize their properties. As our technology advances, we can expect to gain a clearer picture of these enigmatic worlds and the potential they hold for harboring life. The exploration of red dwarf systems serves as a powerful reminder that the universe is far stranger and more wondrous than we can imagine. It is a realm where life, if it exists, may take on forms we can scarcely comprehend, adapting to environments that would spell certain doom for life as we know it. The search for life beyond Earth is a testament to our unquenchable thirst for knowledge, our desire to unravel the mysteries of the cosmos, and discover whether we are alone in the vast expanse of the universe.